All right, I'm going to discuss the strains. Now, in principle, the strain and the stress are not very different. I mean, talking mathematics, strain tensor or the strain or the stress tensor are pretty much the same. So the good thing is everything you have learned about the stress tensor would apply pretty much exactly the same way to the strain tensor. Strain tensor itself is not different. It's just that how you derive it and the physical meaning of that. I mean, the strain is just a physical expression for the stress. If you have a stress applied to you materially, you will not be able to see the stress, but you will see the impact of that as the strain. So basically, the strain you can think of as just some sort of a expression for the stress itself. So they basically physically express something very similar, and mathematically we express them in a similar way. So both of them are expressed in tensors. So today I'm going to discuss the strain tensor. As I said, it should be relatively easy for you. It's just a few concepts that we need to get through in order to be able to understand the strain tensor. So to build the strain tensor, I need to establish a few things. I need to establish three things. First of all, I need to have a description of motion, basically how the object would move. And then I need to have a description for the displacement field. And then I can find the strain tensor. This is the gradient of the displacement field. Just if you remember, I probably just mentioned this as well. Just try to empty the space here. All right, if you remember, the strain, this is what we learned in the finite elements. This is what we learned in finite element A, if you still remember this equation. So the strain was the derivative of the displacement. Now we are discussing a general case. So now we are discussing a situation where you have the strains happening in 3 dimensions. So this is the strain tensor. So this equation would not work anymore. We need to have an expression that is equivalent, which will happen in 3D. So in order to be able to do that, we need to find component for the displacement. Displacement is actually a vector. So we have a vector for the displacement. And then we have an equivalent operator. So in 1 dimension, we have the derivative. In 3 dimensions, we have the gradient operator. So this is the gradient operator. We are going to discuss it in more details later on. I just want you to see the big picture before we get into the details. So first of all, we need to discuss the displacement field. And then we need to discuss the gradient operator. Once we have the gradient operator, we can apply the gradient operator to the displacement field, and we get the strain tensor, basically this one here. All right, so all the discussion I'm going to do today is to introduce the displacement field, the gradient operator, and how to apply the gradient operator to the displacement field to get the strain tensor, a derivative of the displacement. The strain is a derivative of the displacement. This is the big picture, all right? There's just a lot more details into it because we are moving into a lot more components, so this is why. But the big picture is here. Don't lose that. All right. In order to be able to find the displacement field, I need to find the position before and after the motion. So before the displacement has happened and after the displacement has happened. So before the displacement has happened, I'm going to refer to the object with the x vector, x capital, and assuming that the object was in this specific location here, I'm going to refer to the center of the object if you want. So the center of the object would have the coordinate x1, x2, and x3. This is written just like a vector. So this is just a vector. And then I have the current configuration. So I have the original configuration, and then I'm going to have the current configuration. So assuming that this object has moved from here to here, so the center would have moved from here to here. So the original configuration was happening at x capital. The new configuration would happen at x small. So this is at x small. So x1, x2, and x3. All right, it's as simple as that. So there's just a vector to describe the current configuration, a vector to describe the original or the reference configuration. That's it. Now, the current configuration would, in the most general case, be a moving position. So this object would move from here to here, but at time t, I can describe it with x1, x2, x3. But when the time would change, x1, x2, and x3 would also change. So these components for the current configuration are basically functions of time, and they are also function of space. So based on the original configuration, of course, this can be a new configuration. I'm assuming that this object started from here, then it would certainly have moved to another place if the original configuration is different. All right, so I want you to remember that this guy here, the current configuration, is basically a function of time. When the time is equal to 0, x1 small and x1 capital are the same. So at time equal to 0, these two configurations will match. Now, just a quick word about possible displacement fields that has absolutely no impact on the stress case. If you add a constant to the original configuration, the new configuration would be, let me say, probably I say it this way. So if the new configuration is the same like the old configuration plus a constant, then in this case, this is a rigid body motion, right? Just a term. I mean, I'm sure you have heard of the rigid body motion, but this would translate into this expression if we are having a description of motion. The second thing is, if the new configuration minus any random vector b is equal to the old configuration minus the same vector multiplied with some orthogonal tensor, R is a random orthogonal tensor, this is described as a rigid body rotation around the vector b. And if you take b to equal 0, you basically remember that orthogonal tensor would rotate vectors from one coordinate system to another coordinate system. So a rotation around the 0 vector, if you want. I mean, if you remember, the Q matrix will just apply some rotation of the coordinate system. And then if you have a combination of both, so if you have a combination of both things, then in this case, x minus b multiplied with RT added to a constant. This is a translation and a rotation around the vector. So this is a rigid body translation and a rotation around the vector. This is it does not make sense to describe to explain the description of motion and not to tell you these very famous cases. So this is kind of very important description. This is very important motions that you really need to be aware of. All right. So I'm just going to solve one example to clarify things. Do you have any questions before I solve an example? Okay, I'll take this formula. All right. So we have a situation where x small, and this is vector, is equal to x capital added to this value here, k, some constant, multiplied with t, that is time, multiplied with x2, multiplied with e1. Now, I'm just going to expand the components of these vectors so that you can see them. All right? So x is x1, x2, and x3. So this is a vector there, is equal to x capital. So this is x1, x2, and x3. And then you are adding some constant. So I'm just going to write the constant. Remember, x2 is a constant. It's just a scalar. It's a number. X vector would involve 3 components. Just one component, this is x2, is a scalar. So I'm going to write this as a scalar. So this is k, t, and x2. And this is multiplied with the E1 basis vector. So the E1 basis vector is basically 1, 0, 0. All right, so if you want to write this in detail, you'll see that x1 is equal to x1 capital added to kt x2. So I'm just going to write it down. And then if you look into x2, this is equal to x2 added to 0, because 0 multiplied with this constant is going to be 0. And if you look into x3, x3 is equal to x3 as well. So the only changing component with time is x1, x1 small. x2 and x3 would remain the same. Okay, so now we want to use this description of motion. We want to use that to find the new configuration of a unit cube or a unit square. I mean, since we're talking in 2D, since x3 is 0, basically it will not make any difference for us. So we are going to look into a unit square. So how the unit square would move if we use this description of motion. Now, this is the description of motion we are using there. All right. So I'm just going to move into one note here. So you have a unity cube. I'm just going to draw the unity cube. I'm just going to call it a unit square because this is in 2D. I mean, in the third dimension, nothing is happening. So this is x1, this is x2, and then we basically have a unit square. So I'm just going to write the coordinates of the unit square. So this is 0, 0, this is 1, 0, this is 1, 1, and this is 0, 1. Just a unit square. Now I'm going to take every single one of these points and use the displacement field which I've described here. So x1, x2, and x3. So x1 is equal to x1 added to kt x2. And then x2 is equal to x2, and x3 is equal to x3. So I'm just going to use these equations to find the new position for every one of these 4 nodes at time t. All right. So since instead of using the cube, I'm going to use if you want to write this in 3 dimensions, I'll probably just do that, but I'm not going to use it. So this would be 0 again, and this would be 0 again, and this would be 0 here and 0 here. As you can see, it's just a set of zeros, which does not make any sense to calculate because it's just a repetition of zeros. So I'm not going to do this in 3D, I'm just going to do it in 2D. So basically this equation you cannot forget about as well. It doesn't make any difference. All right, so I'm going to take the first point, so point 0, 0, 0, and then point 0, 0, this is x1, capital is equal to 0, and x2 capital is equal to 0. I'm interested in finding x1 small and x2 small. So look into x1. This is equal to x1, which is 0 in this case, and kt multiplied with x2, which is also 0. So x1 at time t is equal to 0. If you do the same for x2, you'll see this is equal to x2, and x2 is already 0. All right, so this is for the first point. Now we want to do the same thing for the second, the third, and the fourth point. So we just repeat the same thing for the 4 points. So the second point is 1, 0. And then this will give us x1 is equal to 1, and x2 is equal to 0. So just use the same equations. x1 is equal to x1, which is 1, added to x2, which is 0, multiplied with 2 with kt. So this is 0, so this is equal to 1. x2 is equal to x2 is equal to 0. So this is x2. So this is the second point. Now let us do the other points as well. So the point 0, 1, you have x1 is equal to 0 and x2 is equal to 1. And then you want to find x1. This is equal to x1, which is 0, added to kt kt multiplied with 1. So x1 now is kt. See, basically x1, if you look into x2, if you look into the first point started at 0, 0, and then it ended as well at 0, 0. So it ended up at 0, 0. So the first point has moved nowhere. It stayed basically in the same place. If you look into the second point, 1, 0, you'll see that it started at 1, 0 and ended up at 1 and 0. So it ended up exactly in the same place. Now, if you look into the third point now, this one here, 0, 1, you see that it started at 0, 1, but ended up at something different. So x1 is kt, and x2 is basically equal to x2 capital, and x2 capital is 1. So if you look into the third point, you see that this third point has ended up at k and 1. So the coordinate has moved to this point here. The new point is kt, comma 1. All right, so this is the new location of the third point. If you look into the last point, 1, 1, you can see that x1 is equal to 1 and x2 is equal to 1. And if you compare things, or if you want to find the new configuration, is x1 equal to 1 added to kt multiplied with 1, and x2 is equal to 1. So this is basically 1 added to kt, and this is equal to 1. So this is the new location for the last point. So the last point started at 1, 1, and then it moved to kt added to 1 plus 1. So in the vertical axis, it did not move at all. It just moved in the horizontal axis. And the square now, the unit square, would look like this after it has moved according to the given displacement field. All right. Basically, this is the old configuration, and this is the new configuration. I probably just try to highlight the new configuration is over here. All right, so the unit square was skewed in this way. Let us move to the next step then. Now we have a description of motion. I want to have a displacement, or description for the displacement. Before I do this, again, I want to explain two concepts. This is something you need to know. Again, if you're studying continuum mechanics, you have usually two descriptions for the material behavior. The first, or the first description is called the Lagrangian description. You probably have heard this in the past, but if you have not, then I'm just going to say it once today. And then you have the Eulerian description of motion. So basically, you can describe the displacement field using a Lagrangian or Eulerian. So the Eulerian one would always relate to the current configuration, and the Lagrangian one will always relate to the reference configuration. So this is the basic difference. So the Eulerian one would always use x1 small. It is the current configuration. The Lagrangian one would always use x1 capital, because it is always about the reference configuration. Now, the Lagrangian one is very useful for solids. So when you do solid mechanics, you always use the Lagrangian one, because the configuration, the original configuration, would still be meaningful if you want to compare the current configuration to it. But when you have large deformations, such as in fluids, the original configuration would be completely, it's of course relevant, but would completely not related, and not related, but probably rather than the original configuration and the current configuration, they can be completely different. They would look very different. So using the original configuration to describe the displacement, you would not get anywhere. So this is why in large deformation, you would use the Eulerian description, and the Eulerian description is all about the current configuration. All right. So since we are doing solid mechanics in our course, we are going to stick with the Lagrangian description of motion. So it is all about the original configuration. So this is basically it. All right. This is just a term. This is just a concept or a term you won't use. Do you have any question about this? I'll take this as a no. I want you to go back to the original picture. See, what I have done so far, I'm still trying to describe the displacement. Now I have an original configuration and the current configuration. I need to find the displacement between the two configurations. So this is exactly what I'm going to do now. The displacement is going to be the new configuration minus the old configuration. So this is basically just a vector minus another vector. So if you remember from vector calculus, this vector joining this point to this point is basically this vector minus this vector. All right, this is just from vector calculus, and it would make perfect sense. So assume that assume that a car is moving along this vector here, axis x. Let us just, for the sake of argument, describe that. And the car was at position 1 at time t equal to 0, and it is at position 5 at time t equal to 3. So what is the displacement of this car? The displacement is 5 minus 1. It's basically 4. All right, so this is exactly the same thing, just generalized into vectors. So it is the new one minus the old one. So this is the displacement field. The current position minus the reference position. This is the displacement field. Now I have the displacement. I'm just going to solve probably one example or two before we move into the gradient operator. This gradient operator guy. Okay, so the deformation or the deformed configuration of a material is given by this vector. X1 is equal to half x1, x2 is equal to x2, x3 is equal to x3. We want to find the displacement field. This is just an example to relate numbers or just to relate things together. So the displacement or the current configuration is x1, x2, and x3. And this is basically half x1, and then x2, and then x3. So this is the current configuration. Of course, the original configuration is always x1, x2, and x3. Now, what is the displacement field? So what we are looking for in this case is u, that is unknown, and u as a vector. So the u vector, u1, u2, and u3 is basically equal to x1 small, x2 small, and x3 small minus x1, x2, and x3. All right, so x1 is half x1 minus x1. So this is going to be minus half x1. And then x2 minus x2 is 0, and x3 minus x3 is 0. Right, so it is minus half x1 and 0 and 0. So this is the displacement field. So this is the component of the displacement vector. All right. Any questions about the displacement vector? See, as I said, it's just you would expect the current displacement minus the original displacement to be the displacement, or the current configuration minus the original configuration to be the displacement, and then you have a description for the displacement. That's all I wanted to say. Okay, so please don't get confused just because you are using slightly more advanced math than the general type of mathematics you have learned in the past. Or it's just vectors instead of just scalars. This is the only difference. Now, we have the displacement field. As I said, we have the displacement vector. We want to apply a gradient operator. Apply a gradient operator to the displacement vector, and then you get the strain. Now, it's not going to be the strain itself. You need to make it symmetric, and in order to make it symmetric, just add it to its transpose, and divide by 2. All right, so this is the strain tensor. This is the equation for the strain tensor. So this displacement to gradient can be obtained using this equation, and the strain tensor can be obtained using half the displacement to gradient added to the transpose of the displacement to gradient. That's it. Now this is slightly, this looks like a big equation, but I'm just going to explain it. It would make sense now. So basically, you take u1, and then you find the derivative of u1 with respect to x1, the derivative of u1 with respect to x2, the derivative of u1 with respect to x3, and you have the first row of your displacement to gradient. When you look into the u2, you take the derivative of u2 with respect to x1, the derivative of u2 with x2, the derivative of u2 with respect to x3, and then you have the second row of your displacement gradient, and then you do the same thing for u3. So the gradient operator, I mean, you are not going to use this for anything except for the display, for the strains. So the gradient operator, but I want you to remember that the gradient operator itself is a general operator. So applying this operator to a function is different than applying it to a vector. But applying it to a vector would be the derivative with respect to x1, the derivative of this whatever vector you have in there with respect to x2, with x3, and so on for the second component, and so on for the last component. So apply it to a vector, you get a tensor, basically. This is what you get. And this is what we call the gradient operator. All right, so this inverse delta operator is called the gradient operator. Now, you only need to learn this in the context of the strain tensor. So it's basically the derivative of the first displacement, the derivative of the second, the derivative of the first with respect to different components. Just like you did in the past, if you remember, this is the derivative of u with respect to x when you had only one u and one x. Now you have three different x's, x1, this is x1, and this is x3. Yeah. So you have x1, 2, and 3. It should have been the other way around. But anyway, you have x1, x2, and x3, and you have u1, u2, and u3. So this equation would not be valid anymore. Instead, you have to use this bigger equation here. Is the derivative of u1 with respect to x1, u1 with respect to x2, u1 with respect to x3. And you get the displacement to gradient. You add the displacement to gradient to the transpose of the displacement to gradient. You multiply with half, you get the strain tensor. This is all. All right. Now, this is one. I just want you to remember that this is one type of the strain tensor. It's called the infinitesimal strain tensor. And this is the type you need, or this is the strain tensor we're using in continuum mechanics when we discuss solids. So this is very useful for solids. And since you are mainly going to deal with solids, so this would work absolutely fine for you. Okay, so this is the strain tensor. This is basically the strain tensor we have been looking for in the three-dimensional case. This guy. All right, I'm going to solve some examples, so things should start to become clear. But before I solve any examples, I just want to tell you that everything we have learned so far about the stress tensor will still be applicable. So if you want to find the normal strain in a certain direction, you multiply with the normal direction from left and right. So if you want to find if you remember, when we wanted to find the normal stress, sigma n is going to be n multiplied with sigma, multiplied with n. We multiplied with n from left and right to get the normal component of the stress vector. We do the same thing for the normal component of the strain vector. And if we want to find the shear component, we multiply with n and n. So this is going to be slightly different. But anyway, this is the normal component. And if you get the shear component, you multiply with n and m. N is a vector and m is a vector, so both are vectors, and you get the shear component of the strain. Now, I want you to understand that there will be different meanings when we multiplied with n and got the normal component of the stress. This was the normal component of the stress, so basically the stress active in the normal direction. When we look into the strain, this is not a component, this is not a stress active, not the strain acting in a certain direction. It is the strain acting in a certain direction, but it has a physical meaning. So the meaning is a change in the unit length in the n direction. And when we do the shear component, it is the change in the angle in the n and m components. So I'm just going to explain it in a slightly more details here. So this is the strain tensor. It's going to be E11, E12, E13, E21, 22, 23, and E31, 32, and 33. So let us start from this strain tensor. We call this guys here normal strains, and we call these guys here shear strains. I think you probably expect that, just similar to the stresses. Now, the meaning for the normal strain is the change in the length. All right, see, if you want to consider the strain in one dimension, if you remember this case here when we had the bar, finite element A again, so the strain is basically the rate at which the displacement changes in the one direction. So the change in the length. The same is correct in this case. So the change in the unit length in the direction of x1, x2, and x3. So the change in the unit length in the x1 direction is E11, the change in the unit length in the x2 direction is E22, and the change in the unit length is this one. And then you have the shear component. The meaning of the shear component is if you have two vectors, x1 and x2, in the original configuration, and then you move to the new configuration, there will be a probably change in the angle. So you'll have, I probably should have used X. And this is what I'm going to do. Not to confuse you, I'm not going to use X1 and X2. Let us assume that you have N and M, so two vectors. They are in the original configuration orthogonal to each other, and you have applied some stresses, so you move this object into a new configuration. In the new configuration, these two vectors will be probably M bar and N bar. So the angle would not be orthogonal. The angle will not be a right angle anymore. It will be just a different angle. So the change in the angle between the old configuration and the new configuration, the change in the angle will be expressed by the shear strength. This is all. So for a general vector, for any vector n, if you want to find the change in the length of the direction of the vector n, you multiply the strain tensor. This is the strain tensor. You multiply the strain tensor with n from left and right. These are all vectors. So you get the change in the length in the direction of n, If you have two vectors, n and m, and you want to find the change in the angle, you can find the change in the angle by multiplying by n and m. Now, the change in the angle is twice this number. It's not just this number, it's just twice this number. So this is basically the change in the angle. Now, the shear strain is this number, but the change in the angle is twice this number.